Hi everyone, I'm Dajin from Interaction Lab at POSTECH. Our study focuses on the critical role of perceptual alignment between spatial, auditory, and tactile stimuli for effective directional cueing. Let's get started. Imagine that your vision is limited. Sound and touch become essential for situational awareness, allowing us to detect targets for aiming or avoid potential hazards. Additionally, when auditory and tactile cues are spatially aligned, the brain seamlessly integrates them, enabling faster and more accurate responses. However, achieving precise alignment between sound and touch is challenging. Stereo headphones can generate high-resolution, omnidirectional sound with virtual spatial audio. On the other hand, tactile displays require many actuators to express many directions. Typical VR controllers have only two actuators and very limited spatial resolution. Here's an interesting, useful fact about human perception. Have you heard of the ventriloquism effects? It's an illusion where the perceived location of sound seems to come from a visual stimulus when the actual sound source is located somewhere else. This effect works well when the audio-visual separation is within 30 degrees in the horizontal plane. But what about between auditory and tactile stimuli? Could this effect benefit us for spatial tasks? That's the question we are excited to explore in this study. So we first aim to quantify the just noticeable difference in direction between sound and touch on the horizontal plane. Then we assess how misaligned cues within the JND impact spatial avoidance tasks. We first conducted a perceptual experiment to quantify the JND. For experimental setup, we placed loudspeakers around the participant in a closed room. We also implemented a vibrotactile belt to deliver a directional tactile cues on their waist. Then we included two signal types for stimulation. The first type is a pure tone, the second type is a gunshot, which is one of the most important warning cues in gaming, military trainings, and our real life. Let me play the gunshot sound. The experimental conditions for their directions are as follows. The vibrotactile actuators were placed at 5 directions. For each tactile reference, there are 7 auditory comparisons. For example, when the tactile reference is at 45 degrees, the comparison sounds are placed from 0 to 90 degrees. When the sound and vibration were played simultaneously, participants should judge whether they originated from the same direction or not. Based on their response data, we can obtain such kind of psychometric function. What's important in this graph is that within the red range of audio-tactile separation, people are likely to perceive the stimuli as coming from the same direction. Okay, let's see the results. First, the JNDs of perceptual alignment increased as the stimulus moved from the center to the lateral side of the body. The values ranged from 26 to 84 degrees, and there was no significant difference between the pure tone and the gunshot conditions. The results of experiment 1 showed that spatial ventriloquism effects occur between sound and touch. So, how does this phenomena benefit us when performing spatial tasks? In the second experiment, we validate the practical effects of physically misaligned but perceptually aligned cues. We designed the spatial avoidance task because people often rely on sound or vibration to quickly avoid potential hazards. Considering a typical gaming setup, we used headphones and virtual spatial audio. The vibrotactile belt remained the same as in the first experiment. Note that participants could not see the directions of the stimuli in the main task. The first experimental variable was the direction of the gunshot sound. The second variable was the alignment between sound and vibration. In the physically matched condition, the directions of sound and vibration are physically matched, so 8 vibrotactile actuators were included in the belt. In the perceptually matched condition, their directions were mismatched but within the JNDs measured in the first experiment. We used only 6 actuators. The front-back condition included 2 actuators at the front and the back. Their directions were mismatched beyond the JNDs. The last one, auditory-only condition, did not provide any tactile cues. This video shows the spatial avoidance task. Participants should move the joystick in the opposite direction to the warning sound. So, what were the results? For the quantitative measures, reaction time, avoidance rate, and directional errors all improved as the audio-tactile cues became perceptually aligned. For instance, the average avoidance rate reached 92% for perceptually aligned cues and 95% for physically aligned cues, without significant difference. When looking into the ideal and actual response directions, the front-back condition showed a different pattern from the other conditions. Their response is biased toward the direction of the tactile stimulus, which is called tactile capture effect. This suggests that when the directional separation between sound and touch exceeds the JND, people increasingly rely on the tactile cues. Similar to the quantitative measures, subjective experiences improved by the perceptual alignment. Cognitive load decreased, usability increased. Interestingly, ease of use and satisfaction received the highest scores in the perceptually matched condition. So we can say that this condition provided sufficient directional information with less actuators, thus enhancing the usability. Okay, lastly, I'd like to leave you with a few take-home points. The perceptual alignment of sound and touch enhances the speed and accuracy of hazard avoidance comparable to the physical alignment. Perceptual misalignment leads to response bias toward the tactile cues. Our study identified tolerable thresholds for misalignment between sound and touch and demonstrate their practical effectiveness for a spatial avoidance task. I hope our study provides a good foundation for efficient and accurate spatial multisensory interface. Thank you for your attention.